So to actually make one of these arrays, the D here stands for Dolph, who was the person who figured out how to use this type of polynomial to do array excitations, and the T is for Chebyshev. The first thing you do is you choose, or specify really, the number of elements and the side lobe level. You could also choose a directivity and a side lobe level. It's a little bit more complicated to back out the number of elements, but there are some figures in your book, figures 6.24 and 6.25, that are curves, like design curves, from which you can figure that out. Step 2 is turn the side lobe level, which is usually specified in dB, into a voltage ratio. And that is 10 to the side lobe level in dB divided by 20. And then you select the order of your polynomial. P is n minus 1, where n is the number of the elements. Then you find the value of that scaling factor that you're going to do on our -1 to 1 window. So you find Z naught. Using one of two equations in our book, 6-73 or 6-82. They both work. Step 5, you calculate the excitation coefficients. You can calculate your excitation coefficients directly using some closed form formulas, which are 6-77A or 6-77B. But fundamentally, what that equates to doing is writing down your array factor in terms of cosine. So remember, we had that being the sum from n equals 1 to m of a sub n cosine of 2n minus 1 times u. That's cosine theta. So you write that in terms of powers of this cosine instead. So you convert it to terms of cosine to the n u, and it's going to have different coefficients. You got to check out, if you want to see a list of what those coefficients are, you can check out the start of section 6.8.3. And then once you have converted the array factor into terms of cosine to the n of u, you make a substitution where cosine of u is going to be equal to z over z naught. Or we already found the right value of z naught. And you substitute that back in to your new array factor. At this point, you've got your array factor written in terms that kind of look like this. A sub 1 times oh geez. Times cosine of u plus a sub 2 times two cosine squared u minus 1 plus a sub 3 times 4 cosine cubed u minus 3 cosine u, and so on. Now, these are just expansions of cosine of 2u here, and this is cosine of 3u. Yeah, and so on. So when you do this, and then you set that equal to the Chebyshev polynomial, and then you're going to scale it. So that's going to be t sub n, whatever polynomial order you're going towards, of cosine u divided by z naught. If you do that, then you find all of the values of these a coefficients, and those are your amplitude weights on the array. After you have done that, you can figure out the directivity and the half-power beam width using the beam broadening factor, which is a measure of how much wider is the main beam than a uniform linear array with the same spacing and element numbers. And then based on that, you can calculate the directivity and the half-power beam width. The beam broadening factor you can find in equation 6-78. And the directivity and half-power beam width are right after that. So that gets you all of your array metrics. Now, this is a long and complicated process, but if you want to do the bonus requirement on project number 3, the best amplitude taper to use is this one. You should use a Chebyshev amplitude taper on your array if you're trying to meet that maximum side lobe requirement.